Karl Schwarzschild was a German officer fighting in World War I. Whenever he had free time, which likely wasn't very often in the war, he would indulge his intellect by writing scientific papers. One such paper actually had to do with Einstein's theory of relativity, published earlier the same year in 1915. Schwarzschild's paper eventually led to the discovery of what is now known as the Schwarzschild radius, or the event horizon of a black hole. Today, I would like to reveal to you the space-bending properties of black holes. Ever since I was a little kid, I have always loved to research things about science, and especially black holes. They've always really interested me, and especially in the past few weeks, I've gone out of my way to make sure I can really tell you guys this stuff. Black holes are actually one of the most studied and least understood phenomena in the scientific world, which is why they're so... I forgot the word I was going to use, I'm sorry. Which is why they're so widely known and widely thought about, widely considered. In order to enlighten you, I will talk about what they are, what scientists can definitively say about them, and what scientists can only theorize at this point. In order to understand something's properties, you must first have an understanding of what that something is. First, I would like to describe to you what exactly a black hole is, and I will do this by telling you what they consist of and how they form. Nola Red, a scientist and frequent writer for Scientific American Journal, says this about black holes. The inner region of a black hole where its mass lies is known as its singularity, the single point in space-time where the mass of a black hole is concentrated. Now, what most people think of as a black hole is something like this, where you see either the big ball of black or just what looks like a hole of black. The problem with this is that these are not actually black holes. This is simply the fact that you can't see what is in the black hole because it's pulling in the light too much. What a black hole actually is supposed to look like is something like this. This right here is the black hole. It is a single point in space-time, meaning that if you were to actually be looking at it, technically, it's not even there. It's just a point, a single point. What you have around here, what is seen as the ball, is just the event horizon, which is where light can no longer escape from the gravity of the black hole. Based on an article from HubbleSite.org, a website dedicated to bringing the out of this world into this world, when a black hole is formed when a star dies, goes through a supernova, and has enough gravitational force to collapse to what is called its Schwarzschild radius, like I mentioned before. Now, this, as you can see, is the Schwarzschild radius, and that over there is the formula for getting the Schwarzschild radius. It's 2 times a gravitational constant times the mass of whatever the star is, or the thing is, over the speed of light squared. Just to put this into perspective for how small these things become, if you were to take the Earth and crush it to the size it would require to be a black hole, it would fit on this dime. That small for the entire Earth. However, despite the fact that scientists actually know how they form and what a black hole is supposed to look like, scientists really know relatively little about these phenomena, which moves me on to my next point. In general, scientists can definitively say only a couple things about black holes. These things are that they affect matter and they affect time. As with anything massive, black holes have a gravitational field that they can exert on everything around them. According to the Associate Professor of Physics at Richmond University, Ted Bunn, a black hole will stretch out anything that falls under its influence, which essentially means as you get closer to it, you will get stretched. Well, that makes sense, given that it's gravity. However, what people don't seem to understand is a black hole's gravity is so strong and so crunched together that the gravity affecting my feet would be different from the gravity affecting my head, and it would literally pull me apart if I were to be standing 6,000 miles away from it. I would still be dead because it would pull me apart. That's the power of a black hole's gravitational field. Along with stretching out matter, black holes also stretch out time. For For example, in another piece from HubbleSite.org, if you were to drop a clock into a black hole, you would visibly see the hands on the clock slow and eventually stop altogether before disappearing into the event horizon. This doesn't mean the clock isn't working, although it probably wouldn't in a black hole. It just means that the light from the clock isn't getting to us anymore. And so it's slowing down and stopping literally in front of our eyes. Although scientists have been unable to definitively prove all that much about black holes, they have been able to theorize a great deal of information about these things. Two of the most important theories about black holes are the possibilities of time travel and interstellar space travel through the use of wormholes. First of all, Stephen Hawking himself has said time travel to the future, only the future, is possible through the use of black holes. Essentially what happens, oh, this is a bit higher than I expected. Essentially what happens, if you get into a rocket ship and fly your way to a black hole, if you go and you start swirling around all of this up here without actually going into it, because of the gravity and the light being pulled in, time for you would go slower. You would spend maybe a year out there and come back to find out that 3,000 years had passed here, simply because everything was getting pulled into there, including the time distortions. Now, when it comes to regular old space travel, however, it's a bit more complicated. First of all, in order for this theory to actually be true, space-time has to be what is called curved, which essentially means everything, even though you're going straight, space-time curves itself, like this. Even though you're going straight this whole way or this whole way, you curve back around. And then what happens here, it's kind of hard to tell, but this is a hole leading to the other side. This is a black hole. And it distorts space-time so much, it's so heavy, that it pulls you all the way to the other side without going through the intervening space. That's the sort of thing you see in Star Trek or in Galaxy Quest. That's a good reminder of that movie. This is the idea behind a wormhole. And that's why it's a little more complicated than time travel, is it requires this space is curved theory, which is actually part of Einstein's theory of relativity as well. Throughout this presentation, I have told you what a black hole is, what science can definitively prove about them, and what theories are currently under investigation. Black holes will always be a subject of fierce observation for the scientific world, and it isn't going to stop until all of their secrets have been revealed. Thank you.
I think I forgot to remind people for Nick's speech who was doing these different evaluations. Daniel's supposed to do the written evaluation. I don't think Daniel's here today. Frank is supposed to do the oral evaluation. Frank, could you share your thoughts with us, please?
Yes. So his overall point, his thesis was about black holes and their space-bending properties. He had very clear transitions, and his visual aid was well defined. It's evident that he put much thought and practice into this. As far as what he needed to improve, there was nothing except for that he addressed a mistake early on, and with one of the visuals, he pointed out that he made not a mistake, but it wasn't what he thought. Maybe leaving that out would have, had this perfect presentation. My overall thoughts were that this was, in my opinion, one of the best speeches I've heard, not just in this classroom, but anywhere as well. He put a lot of effort to it, and yeah, it was very good.
All right, kicking butt and taking names, as they say. All right, Nick, I thought you did an excellent job identifying what your subject was. You told us that interesting story about the origination of the theory there. You identified the topic very clearly. Maybe I think we could use a little bit more justification. Your personal experience, for instance, as a way of building some credibility is fine. Why is this important to us? Why is it meaningful? Why are people studying it? I think we need a little bit more of that at the beginning, but you have an excellent layout of what the structure is going to be. So there's a stellar preview in the presentation, and I'd agree with Frank. I thought the transitions were really effective. They moved us from point to point very clearly. Nobody's getting lost while you're presenting information. This is a good example of a speech that's filled with a lot of, let's say, theory stuff. You've got good quotes and technical information that you are presenting in the speech, but you usually do a solid job of explaining it and making it easier for the audience to relate to. There are a lot of examples of things that you've done, that you've added to the presentation that make it easier for people to understand, more interesting to listen to. So you don't just keep it with the quote that you've got here, but then you kind of give us a personal visualization of those ideas, the Earth being crushed to the size of a dime, for instance, or the idea of how the wormhole would be involve some travel. The only issues that I had on the visuals were sometimes the images are a little indistinct because they're fuzzy. I think you probably blew them up a little bit more than was practical, and there might be some way to fix that. That's a technical kind of thing. I'm not exactly sure what advice I would give you on that. Sometimes it helps to shut the lights off to give us a little bit more contrast. And there were only a couple of them that were that way. You could maybe see, and even the ones that were that way, it wasn't that big a deal. The one that had the formula on it, for instance, we could still see the formula. I think people might have had a little bit of trouble, at least I did. I was an old man, sitting in the back here in this blue up there. I was having a little bit of trouble seeing the wormhole in the curved space slide that you had. I figured out that it was there. I squinted a little bit sideways. It's that, like I said, but those are minor quibbles. Everything else I thought was put together really well. And you also delivered it very effectively. I thought you did a good job talking to the audience. I understand what Frank's talking about, sometimes drawing attention to a mistake that you made. Nobody else is going to notice that mistake. You're the only one who notices it. And so it's just a little more practice, and it wouldn't be something you just shrug it off to yourself and don't worry about pointing it out. All right, thank you.